So we're going to be talking about coordination compounds. Transition metals, they tend to form complex ions. And I have here like an example of how a complex ion will look. You have a metallic center, and to that center, you will have ligands bonded to it. This specific one has 6 ligands bonded to it. We can have different number of ligands as we will see in a little bit. So when you have this metallic center bonded to these ligands, you might have an overall charge. That overall charge, right, will make this complex here a complex ion. It's an ionic part because you have an overall charge. In my example, I have plus n, and n can be any number. That charge for the ion, it's not only a positive number, it can also be a negative complex ion. That can also happen. If your complex ion has a positive charge, you will have negative counter ions to make a neutral compound. That neutral compound, when you have your complex ion and the counter ions with opposite charges, will form what is known as the coordination compound. If you have the metal bonded to the ligands and you have an overall charge, that is the complex ion. If you have that complex ion bonded to an ion with opposite charges, you will have a neutral charge because you will have the same number of positive and negative charges. In this example, the positive is the complex ion, the negative is the counter ions, and then when all of them are bonded together, you will get the coordination compound as neutral. So remember that if you have your complex ion with an overall charge of positive, the counter ions will have negative charges. But if your complex ion has an overall charge of a negative number, then your counter ions will be positive. Okay? They will always have opposite charges. The ligands that you have bonded to the metallic center, they will be classified as Lewis bases. So just to review, Lewis bases are compounds that can actually donate a lone pair of electrons. So for your ligands to bond to that metallic center, your metallic center is electron deficient because you have metals as positive. When they lose electrons, they will form positive ions. And then your ligands, those Lewis bases, they have extra pairs of electrons that they can donate to the electron deficient metallic center. And that's how the ligands will bond to the metallic center in your complex ion. So I have some examples here, actual examples. So you have the first one is just an example of the complex ion because you have cobalt, it's your metal. You have 6 ammonias, NH3, right? And then you have an overall charge of +3. So you have your overall charge that represents a complex ion. Now on the right side, you still have the cobalt. You have 6 ammonias bonded to that cobalt. So that's your metallic center, NH3. It's a Lewis base, so you have 6 of them bonded to that metallic center. And now you don't get to see an overall charge because you have Cl3. Those 3 ions of Cl are your counter ions. So your complex ion will have a positive 3 charge, but then if you have your 3 counter ions, your chlorides there, they will neutralize those 3 positive charges with your 3 negative charges from your 3 chlorides, and now you have your coordination compound. Those those counter ions, they are not the ligands. The ligands are directly bonded to the metallic center, forming the complex ion, and then those counter ions are just there to neutralize that overall charge from your for your complex ion. If the ligands are Lewis bases because they're donating electron pairs, the metal electron deficient is considered a Lewis acid because it's accepting the electron pairs that the Lewis bases are donating. The bond between the metal, the Lewis acid, and the ligand, the Lewis base, is a coordinated covalent bond. A coordinated covalent bond is a bond where both electrons are coming from the same substance. When you have a covalent bond between two hydrogen atoms, right? Each hydrogen atom has one valence electron, and they will share, those two hydrogen atoms will share those two electrons, forming your covalent bond. Each one is donating one electron to form the covalent bond. When you have a coordinated covalent bond, both electrons are coming from the same substance, which in this case will be the ligand. So your metal is a positive electron deficient. The ligand is a Lewis base with a pair of electrons, and then both electrons in that chemical bond are coming from the ligand. So two electrons are donated by the ligand. So let's talk in general about ligands, or the Lewis bases that are forming these complex ions with the metals. We have different types of ligands, and the types of ligands are classified here depending on how many pairs of electrons they are donating to the metallic center. So we have the monodentate. That's when your ligand is donating only one pair of electrons. And the example is the same one that I used with the cobalt. Okay? It's ammonia. So ammonia, when you draw the Lewis structure for ammonia, you have the nitrogen, and then you have single bonds connecting the three hydrogens to the nitrogen. And then to complete to the octet on that nitrogen atom, you need a lone pair of electrons. Okay? So ammonia has that lone pair of electrons that can be donated to the electron deficient metal. Since it's just one pair of electrons, then that will be a monodentate ligand. The second one is bidentate, and for those we have two pairs of electrons that are donated, and we have an example right there, which is oxalate and also ethylene diamine. Anything that can donate more than two pairs of electrons will be considered a polydentate ligand. And we have an example right there. It's a very bulky, big compound. The oxalate ligand here should have negative charges, one in each oxygen right here, or it will have an overall charge that is a negative 2. So here we have more specific ligands. We have common ligands, and these are just some of them. Then you will see that later I will give you a long list of ligands arranged in a specific order, which we're going to be using to find out some information about these coordination compounds. So we have ligands or Lewis bases here, the chloride, cyanide, we have thiocyanate, we have oxalate, which we already saw, we have water, ammonia. From these ligands, you need to remember the charges. We have the chloride, everything on the left side of the list, it has a charge, and we have neutral ligands, water and ammonia on the right side. We will get a longer list. Okay? It's not just these ones here, but these ones are the ones that I'm using in the next example. So you have them right here, so you can refer to this page when you're solving the next problems. So coordination number is something that we're going to be using because depending on the coordination number, we will have different coordination compounds. Okay, and the coordination compounds, they will have different properties depending on this coordination number. So that coordination number we're going to determine depending on how many ligands we have bonded to the metallic center. It's not how many bonds, okay? You're gonna have a double bond between the ligand and the metallic center, and that still counts as one. This works more like number of electron groups around that metallic center than actual number of bonds. So that's how we're going to be determining like the coordination number. It's how many electron groups we have around that metallic center. Remember, like in this case, our electron groups are going to be single, double, or triple bonds. Okay? There are no lone pairs of electrons around that metallic center, at least for the examples that we're going over. So we have a list of most common coordination numbers, 2, 4, or 6. So all of this is very general because we're going to focus on those octahedral complexes at the end. Those are the ones that we're actually going to be looking at the properties, how the electrons are moving around those coordination compounds, in which orbitals, and all of that. So we have coordination number 2, that will be a linear complex. We have 4, which is going to give a square planar configuration, and then 6, which is going to look like an octahedron. The generic example that I give you in the very beginning with that M representing the metallic center and all 6 ligands bonded to that metallic center, that represents an octahedral coordination compound. So we're going to start by looking at the oxidation state of the metal in these compounds here and the coordination number, so we can check how that coordination number works. Very important for you to see that all of the metals in my examples are transition metals. So that metallic center that we have in these complex ions or coordination compounds are always from metals from the transition metals. We need to have enough orbitals for the electrons coming from the ligand to be placed. Okay, so that will happen with transition metals. So the first example, I'm going to do 2 and then I'm going to leave the other 2 for you to solve. I'm doing the first one. Okay? So the first one, we have chromium, we have 6 waters. Okay? Those 6 water molecules are bonded to the chromium. So let's work on finding the coordination number first. So coordination number is telling you how many ligands are bonded to the metal. So from the formula, you can actually determine that coordination number. So let's use coordination number here. And look, you have 6 water molecules bonded to that chromium. It means that your coordination number for this specific example is 6. Now, oxidation state for the metal. Let's check that. So to determine the oxidation state of the metal, you have to check different things. For example, all of these here are complex ions. Okay? So you have an overall charge for your complex ion, which is positive 3. Okay? Now, I'm going to write down an equation to solve for that oxidation state for the transition metal. This will be equal to plus 3. And that plus 3 is the overall charge of your complex ion. Now we have 6 water molecules, and each water molecule has a charge of 0. You can refer to the list of ligands that you have. You have a list of ligands where you have ions with -1 charge, you have oxalate with -2, and then you have water molecule and ammonia, both with 0 charge. They're neutral. You don't have an overall charge for water. You don't have an overall charge for NH3. They are neutral. So the water molecule has a charge equal to 0. Since you have 6 of them, right, each one has a charge of 0. And then we're going to add to that an X because we don't know, right, the charge of the chromium in that complex ion. So what we're actually trying to determine is the charge of the chromium. So I'm going to write down my chromium as an X. That X represents the charge of the chromium. So you can solve your equation. You will see that 6 times 0 is 0, and that's equal to 3, which means that the oxidation state for chromium in this specific complex ion is positive 3. So I'm going to do now the second one, and then you can do the last two. So for the second one, we have cobalt, and that cobalt is bonded to 3 ammonias and 3 Cls. You see that chloride that you have right there is not a counter ion. It's not a counter ion because it's inside of the bracket and you have an overall charge. So what you have right there, it's a complex ion with 2 different ligands. Okay? If the chloride is a counter ion, it will be outside of the bracket because it's not part of that complex ion. So again, I'm going to start writing my equation to find out let's find the coordination number first. Coordination number, you have your cobalt and you have bonded to that cobalt 3 ammonias and 3 chlorides. So your coordination number for this example is also 6. It's just the total number of ligands that you have bonded to that metal, and that is 6 because you have 3 ammonias and 3 Cls. Now let's find out the oxidation state for cobalt in this example. So I'm going to start writing my equation again. The overall charge for the complex ion is -1, so let's do that. To -1. Now you have 3 Cls, so that's 3. Cl, right, it's the ion of chloride with a charge of -1. You can refer to the list of the ligands that you already have. The examples that I'm using here are ligands that you have in that short list right there. So the charge for Cl is -1, and I'm writing that in this parenthesis here. You have 3 of them, so that will be a total number of 3 negative charges. And I'm adding to that 3 NH3, it's a neutral ligand with no charge, similar to water, so I have 3 times 0. And then we're missing the cobalt, which is what we're trying to find out, so I'm going to put X for cobalt. It's just one cobalt, so I'm using just X. When you add all of those numbers, oxidation numbers together, they should add up to the overall charge of that complex ion, which is -1. So you have 3 times -1, that will give you -3. You have 3 times 0, that will give you 0. So this will be simplified to that. And now you can solve for X, which means that you have to move that 3 to the other side of your equal sign. And that will give you X equals 2 plus 2. You need 2 positive charges in that cobalt, metallic cobalt, because you have 3 negative charges from the chloride. The overall charge is -1. So you have 3 negatives, 2 positives. When you add those two together, that will give you -1, which is the overall charge of that complex ion. Now for the third example, the last one, you have ammonia again, which is a neutral ligand. So for that one, you assign a charge equal to 0, and you solve everything in a similar way to get the charge of the silver. In copper, the third one, you have a ligand right there that has a charge. So remember, check the list of ligands that you have. For Cn, you have a -1 charge. So you have 4 of them. That will be 4 times -1 plus the X that you have for copper, and all of that will be equals to -2. And you can solve for X to check the oxidation state for copper. And similar for silver, these last two, right? For the first two, we have a coordination number equal to 6. For the last two, you're going to have a coordination number that is different from 6, because you don't have 6 ligands for those two.